You know that old comforting saying we've all heard a million times?
Hmm.
A watch pot never boils.
Oh, yeah. The absolute worst feeling when you're just standing there hungry.
Right. We all know what it means. It's just this psychological trick of impatience. When you're standing there in your kitchen, staring at a pot of water, waiting for it to heat up so you can make pasta, it feels like it takes an absolute eternity.
It really does.
But I mean, in our everyday macro universe, that's entirely in your head. Whether you stare at the water, whether you look away, whether you leave the room entirely, the the rigid laws of thermodynamics are just at work in the background.
Exactly. The burner transfers kinetic energy, the water molecules vibrate faster and faster, and the temperature rises.
Right, the physical processes of the universe at our human scale, they really don't care about our attention span. That water is going to eventually boil completely, regardless of whether you're looking at it or not.
Yeah, the macro universe just marches on independently of our gaze. Classical physics is incredibly stubborn that way. An object in motion stays in motion, heat transfers from hot to cold, and systems just evolve over time with or without an audience to appreciate them.
But, and this is where everything we think we know gets completely turned upside down. When we shrink our universe down, when we leave the kitchen and zoom all the way down to the subatomic quantum scale, this comforting common sense rule completely shatters.
It breaks entirely.
Yeah. In the quantum realm, if you stare at a boiling pot, it physically will never boil. And I really want to be clear to you listening right now, that is not a metaphor. It's not a psychological trick. If you watch a quantum system, it literally freezes.
It's an incredibly profound physical reality. I mean, we were talking about a proven law of nature. It's a literal intersection where mathematical probability and physics collide to demonstrate that the mere act of observation freezes time for a particle.
And it's called the Quantum Zeno Effect. And the goal of our deep dive today is to explore the notes, the research, and the underlying mechanics of this bizarre phenomenon. We're going to look at how mathematically observing a particle physically stops it from changing. Okay, let's unpack this.
Let's do it.
Before we can really wrap our heads around how looking at something freezes it in time, we have to understand what a particle is actually doing when we aren't looking at it. We need to define that unobserved state.
Right, the baseline.
Exactly. So assuming everyone listening knows the basic premise of superposition, that a particle isn't just in one place or another, but exists as this sort of cloud of probabilities, how does that cloud actually evolve?
Well, to understand the freeze, we must first look deeply at the motion itself. And the motion of a quantum probability cloud is governed by the Schrödinger equation.
Okay.
So when a quantum system, like say an electron or a trapped ion, when it begins to transition from its initial, say, let's call it state A, into a new state, state B, it doesn't just abruptly teleport.
Right, it's not magic.
No, exactly. The probability wave evolves. And what's fascinating here is the specific mathematical curve of that evolution.
The curve.
Yeah. At the very beginning of the transition, the probability of the particle moving to state B doesn't grow linearly, it actually grows quadratically.
Okay, wait, let me stop you right there because we really need to make sure the math is crystal clear for everyone. Quadratic growth versus linear growth. How does that actually translate to the timeline of the particle?
Okay, so let's look at the numbers. Linear growth means if you wait twice as long, you get twice the change. It's a steady pace.
Like walking a mile in 20 minutes, so half a mile takes 10 minutes.
Exactly. But quadratic growth relies on the square of the time elapsed. So if the time is infinitesimally small, say just a tiny fraction of a nanosecond, you are squaring a tiny fraction.
And squaring a fraction gives you an even smaller fraction.
Precisely. Squaring a tiny fraction results in an even tinier fraction. This means that at the very start of its journey, the probability of the particle remaining in state A is overwhelmingly close to 100%. Meanwhile, the probability of it having reached state B is incredibly sluggish to get off the starting line. It is mathematically paralyzed for those first few fractions of a moment.
Oh, okay, I see. So it's not like a light switch instantly flipping from off to on. It's more like a dimmer switch slowly sliding up. And for a tiny fraction of a second, the room is still mostly dark, with just the tiniest hint of light starting to grow.
That is a perfect way to visualize it. The darkness is state A. The brightness is state B. When the physical process begins, the slider is indeed moving. But because of that quadratic mathematical curve, it's still overwhelmingly dark for those initial moments.
It takes time to build momentum.
Right. The change is a gradual buildup of probability amplitude, and it's heavily weighted toward the starting position.
Okay, so we have our dimmer switch moving up. But then we introduce the observer. We introduce the act of measuring this particle. And this is where that smooth, wavy transition gets violently interrupted, right? The universe essentially forces the wave to collapse. It forces the particle to make a definitive choice. Are you state A or state B?
Yes. The wave function collapse is really where physics starts to feel hostile to our intuition.
Definitely.
Measuring the system destroys the superposition. The particle can no longer be a smoothly evolving cloud of possibilities. The universe essentially corners it. It demands a definite, concrete answer out of a non-binary cloud.
Wait, let me challenge that phrasing for a second. When you say the universe corners it because someone looks at it,
Yeah.
it sounds incredibly anthropocentric, like the universe actually cares that a human being with eyeballs just walked into the room.
Right, right.
Does human consciousness actually matter here, or are we just talking about, a photon from a lab instrument bumping into an electron?
That is such a vital distinction and honestly a major source of confusion in popular science. We need to look at the actual mechanism of quantum decoherence. Observation in quantum mechanics does not require a sentient mind.
Okay, good to clarify.
Measurement is simply interaction. When a microscopic quantum system interacts with a macroscopic system, like a laser, a magnetic field, or a detector, the delicate phase information of the quantum wave bleeds out into the chaotic environment.
It gets overwhelmed.
Exactly. The pure, evolving wave is destroyed by the sheer thermodynamic noise of the measuring device. The interaction itself is what forces the probability to collapse into a definite state.
So going back to my analogy, the dimmer switch just gets ripped off the wall by the sheer force of the interaction, and it becomes a regular definite light switch again. You're either on or off.
That's it. Now apply the math we discussed a moment ago. If you measure the particle immediately after it begins its journey, right as that dimmer switch just starts to move, the mathematics of that quadratic curve dictate it will almost certainly collapse back into state A.
Because it hasn't had the time to build up enough probability to become state B yet.
Precisely. The vast majority of the probability wave is still sitting in the darkness of state A. When forced to choose due to decoherence, the particle just snaps back to the starting line.
Here's where it gets really interesting. Because physicists didn't just, calculate this on chalkboards and call it a day. They actually took it into the lab. They asked, well, what happens if we measure it again and again and again? If you measure that particle and then a fraction of a nanosecond later you measure it again, it collapses back to state A. And if you repeat this measurement millions of times per second, you constantly force that probability wave to reset. You never give the dimmer switch enough time to slide up past that incredibly slow quadratic starting curve.
We can actually point directly to David Wineland's groundbreaking experiment for this. This was back in 1989 at the National Institute of Standards and Technology.
Oh, wow. So this isn't even new theory.
Not at all. His team trapped beryllium ions in a magnetic vacuum. They used a radio frequency pulse that was specifically designed to smoothly transition the ions from a lower energy state to a higher energy state.
The state A to state B transition.
Exactly. Left alone, the ions would smoothly make that transition. But Wineland's team introduced a second element. They used short pulses of ultraviolet laser light to measure the state of the ions.
They were constantly checking on the pot of water.
Yes, they bombarded the ions with these ultraviolet measuring pulses, and the results perfectly matched the math. The more frequently they pulsed the laser meaning, the more often they measured the system, the less the ions transitioned. By observing the system continuously, millions of times a second, they literally trapped the ions in their original state.
It's almost like constantly refreshing a web page that's trying to load. By hitting refresh millions of times a second, you never actually give the page enough time to pull the data from the server so it just stays blank forever. You're effectively stopping time for that web page.
That's a great way to put it. Every time you hit refresh, every time the UV laser hits the ion, you wipe out whatever progress the probability wave has made toward the new state. The particle is trapped by your measurement. You are successfully stopping time for that particle by denying it the unbroken span it needs for the probability of change to actually build up.
That is just a staggering physical reality.
Yeah.
The wave function just keeps resetting, collapse to A, collapse to A, collapse to A. But, if human instrumentation can literally freeze an atom in its tracks and stop it from evolving, what does that mean for our entire concept of time? We experience time as this absolute thing. The clock ticks forward no matter what we do.
If we connect the bigger picture, we have to look at the perspective of the thinkers and students at Math for All who dissect the philosophical implications of these equations.
Okay.
For them, the quantum Zeno effect unravels one of the deepest mysteries in physics. It suggests that the arrow of time, the idea that time is this absolute independent river flowing endlessly forward in the background of reality, might just be a fundamental illusion.
Wow. Because if extracting information from a system literally stops that system from changing, time isn't an independent river at all. It is inextricably tied to the act of observation.
Exactly. Time, at its core, is just the measurement of change. Without change, there is no time. If continuous observation can literally stop an atom from decaying or altering its state, it heavily implies that change is a product of information gaps.
Information gaps.
Yes, the progression of the universe only occurs in the dark spaces where information is not being extracted.
Gaps in information, meaning literally the things we in our instruments aren't seeing.
Yes. The universe only moves forward because we aren't looking at every single pixel of it all the time. Change happens in the dark. When we extract information constantly, when we close those gaps through measurement, the change stops. The time stops. It literally requires us to look away for reality to progress.
Wait. So time isn't a ticking clock on the wall that runs independently of us. It's more like a video game engine that only bothers to render the graphics and move the NPCs forward when the player's camera's pointing away. The rendering is the passage of time.
It's similar, yes. In a standard video game, to save processing power, the engine only calculates the heavy graphical details when you are interacting with them or looking at them.
Right.
In the quantum universe, it is almost the exact inverse. The processing of change, the actual evolution of the wave function, only happens when the system is isolated, when it is strictly unobserved.
Oh, that's wild.
When you point your camera at it, when you interact and extract information, the system locks into a defined static state. The rendering halts, the gaps in our attention, our lack of measurement, provide the actual breathing room the universe needs to evolve.
The rendering halts when we look. That completely shatters the macro worldview we started with in the kitchen. But, as mind-bending as this dorm room late-night philosophy is, we have to bring it back down to earth.
Yeah.
Because we aren't just doing this in a vacuum chamber in 1989 to win arguments about time anymore.
No, not at all.
This cosmic glitch is actually being built into modern machines.
It really is. It has transitioned from a profound philosophical revelation into an essential engineering tool. We are currently utilizing it to stabilize the most fragile technology on the planet.
So what does this all mean? How does a glitch that freezes time actually manifest in human technology today?
Well, the quantum Zeno effect is currently being used as a foundational element in building error correction codes inside quantum computers.
Okay, quantum computer.
Right. Quantum computers derive their massive processing power from utilizing these incredibly fragile quantum states, the superpositions. The problem engineers face is that these superpositions are exceptionally delicate. Any stray interference from the outside world, a microscopic fluctuation in temperature, a stray cosmic ray, or even just ambient electromagnetic noise can cause the qubits to decay, lose their information, or flip to the wrong state.
Because they need to stay in that fluid, dimmer switch wave state to perform their complex parallel calculations, but the physical environment constantly threatens to collapse them accidentally.
Exactly. The environment acts as an uninvited observer. So, to combat this, engineers deployed the Quantum Zeno Effect. They use continuous, highly strategic measurements to freeze the desired states in place.
But wait, didn't we just establish that measuring a quantum system destroys its superposition and forces it into a definite state? If they're measuring the qubits, aren't they wiping out the very quantum calculations they're trying to perform?
That is the genius of quantum error correction. They don't measure the entire data state of the qubit directly.
Oh, how does that work?
They use what are known as ancilla qubits, or helper qubits, connected to the main data qubits. They measure specific properties, like the parity between two qubits, without extracting the specific phase information of the calculation itself.
So they're peaking without fully looking.
Basically, yes. They are measuring the error syndromes. By continuously extracting just enough information about whether an error has occurred, they essentially hit the refresh button on the qubit's baseline stability.
Oh, I get it. They are continuously observing the boundaries of the system to freeze out the unwanted decay while leaving the data inside entirely untouched. They are hitting refresh millions of times a second on the parts of the computer they don't want to change.
They're literally utilizing the pause button of the universe. By forcing the wave function of the error states to constantly reset back to zero, they keep the most advanced computers humanity has ever built stable enough to actually function. It is a masterful manipulation of quantum mechanics.
That is incredible.
But stepping back from the engineering for a second, it really brings us to a profound conclusion about our broader role in the cosmos. The act of measurement is not passive.
We aren't just sitting in the audience eating popcorn while the cosmic movie plays out on the screen.
Not at all. Our measurements, our extraction of information from the environment actively shape the evolution of reality. We are the editors cutting the film. The clock only ticks when we let the universe blink. This raises an important question. If our observation dictates the flow of state changes, what is the true nature of our relationship with reality?
Wait, if we're the editors cutting the film, does that mean the universe is essentially relying on our blind spots to function? Like without our ignorance, without us blinking, reality would just hit a brick wall?
The physics strongly imply that macroscopic progression requires a lack of absolute certainty. Think about it. If some hypothetical entity could observe every single quantum state in the universe simultaneously, constantly extracting all phase information and collapsing every probability wave, the direct implication of the Zeno effect is that the entire universe would freeze.
It would just stop.
Yes, it would be entirely static. The universe relies on our inability to see everything at once. It relies on the gaps. It relies on the fact that macroscopic beings and instruments simply cannot measure all the pixels at the same time.
The clock only ticks when we let the universe blink.
Hmm.
That completely reframes how we experience our day-to-day lives, even when we are just standing in the kitchen waiting for water to boil.
It really does.
Okay, let's pull all of this together for you listening. We started with a simple proverb, right? A psychological trick about impatience. We journeyed down into the subatomic world where we discovered that particles don't make simple binary choices, but instead ride mathematical waves of infinite possibilities.
And we examined the mathematical reality that these waves build up quadratically, meaning they start incredibly slowly. And we learned that the very act of extracting information through measurement acts as a cosmic interruption, forcing the waves to collapse.
Right. By constantly checking on a particle, we reset its probability wave to that incredibly slow starting point, trapping it in its original state and effectively stopping time.
Which reveals a staggering paradigm shift. The arrow of time isn't an unstoppable force rushing past us independently. The flow of time, the ability for the universe to change and evolve, exists strictly within the gaps of our information.
Our act of extracting information is what pauses the universe, and our blind spots are what allow the universe's clock to tick. We are the reality editors.
It fundamentally redefines what it means to be an observer in a physical universe. The interaction required to observe is the very mechanism that locks reality into place.
But I want to leave you with a final thought to really mull over. Something to explore on your own that pushes past the lab equipment and the quantum computers. We know now that observing a particle forces it to choose a state, and that freezing it with constant observation stops time.
Right.
And we know the universe only moves forward in the gaps of our information. So what exactly does the universe look like in those rare, entirely unobserved moments? Think about a localized space where nothing is measuring anything. When absolutely nothing is looking, measuring, or extracting information, does the entire cosmos just dissolve back into a chaotic, mathematical cloud of infinite possibilities, entirely formless, just waiting for something to open its eyes?
A universe comprised purely of mathematical potential, entirely fluid, just waiting for an interaction to force it into existence.
Thank you for joining us for this deep dive. The next time you blink, really appreciate it, because in that tiny fraction of a second, you are literally letting the universe move forward. See you next time.